Hi, my name is Tamzidul Mina. I am a robotics R&D staff at Sandia National Labs. The topic of my presentation today is beacon-based distributed structure formation in multi-agent systems. Autonomous structure formation by large-scale multi-agent systems has enormous potential in applications ranging from building habitats for humans on other planets, building makeshift dams for water diversion containment during flooding, to developing programmable matter for manufacturing in the future. Previous work have repeatedly shown that the complexity of multi-agent system self-organization in terms of coordination, control, communications grows exponentially with increasing number of agents in the system, which is the current research focus in the area. Towards this work, our proposed method includes a robust shape representation and distributed structure formation strategy achievable by local sensing, communication, and bidding as required, and allowing already settled agents to guide free-moving agents towards the formation frontier. This addresses the issue of increasing computational requirements with an increasing number of agents, promoting a highly scalable system in the context of large-scale implementation. Therefore, our method is in direct contrast with prior works on centralized controller strategies, large-scale bidding and consensus-based approaches, and search-based path-inefficient methods previously proposed in literature. A high-level overview of the methodology is presented here. We use a connectivity graph to describe an arbitrary geometric makeup of a structure. Node connections from node M to N is represented by its relative distance, elevation, and azimuth, which form the row column element in the adjacency matrix. Each agent in the system is aware of this matrix. The structure formation process is achieved by agents independently following a finite state machine, starting with random walk, moving towards the structure, following a surface gradient broadcasted by settled agents, and locally bidding to settle if needed. Settled agents act as a beacon to attract free-moving agents by generating a surface gradient. Settled agents with all neighbors settled broadcast the gradient throughout the surface. Beacon agents follow the beacon settling algorithm to sequentially help settle all its connected neighbors on the graph using the adjacency matrix. Surface gradient generation is initiated for each of the settlements, and settlement information is broadcasted locally for surface following agents. The surface gradient generation is initiated by beacon agents and inspired from morphogen gradients. The lowest count from a settled neighbor is implemented at each hop by settled agents and locally broadcasted. These local broadcasts throughout the structure help guide free-moving agents towards beacons. Multiple surface following agents reaching a settlement location undergoes a local bidding process using its distance traveled and a distance to the settlement location. The winner settles at the location while the rest move on. Motion control is achieved by potential functions to maintain inter-agent spacing, collision avoidance, and structure maintenance. Specific rules are also set for agents to escape possible stagnation points. Our validation case includes planar structures, a circle and a pentagon, formed by 30 agents in a closed environment. A beacon agent is placed to initiate the formation process, shown in red. Agents successfully traverse the boundary following the surface gradient visualized by the color scheme to reach a settlement and eventually form the structure successfully. We repeat our validation for 3D structures, a cylinder and a pentagonal prism. Successful structure formation is achieved for both cases. Agents are observed to successfully traverse soft corners of the structures. The proposed system utilizes a completely distributed process where each agent determines its own actions based on received communication and observations of immediate neighbors. The system is concluded to be robust against agent motion failures. Since any position in the structure may be taken by any agent, the shape formation process will continue and complete with the remaining agents as long as their paths are not blocked by disabled agents. For scalability, we show the mean and standard deviation plot of the cylinder and pentagonal prism formation repeated 5 times for each n. Larger structures tend to have a larger number of active beacon agents compared to small structures, aiding the formation in multiple fronts. Therefore, the difference in required time step between n equals to 30 and n equals to 360 structures is observed to be fairly small. Although further investigation is required on more complex shapes and a real-world implementation consideration, based on our current findings, we conclude that the proposed method at its current stage is highly scalable in the multi-agent domain for the formation of simple building block structures. To conclude, a highly scalable self-organizing strategy for large-scale multi-agent systems is proposed to form prescribed shapes and structures using local communication and sensing with immediate neighbors that is robust to robot failures. The formation process was successfully validated with shapes and structures containing continuous boundary surfaces and soft edges. For future work, the proposed system is currently in its early stages of development. We plan to focus our efforts on agent surface following around sharp corners on the structure to improve robustness to structure geometry and real-world implementations for direct comparison with existing methods. Thank you.